Having covered everything that was needed for the second midterm, we'll move on to some just a review of some applications and some standard problems that you could expect to see in your midterm. I think the easiest thing to review would be L'Hopital's rule, the use of L'Hopital's rule. So let's look at this. So this is actually a typical problem that is asked very often, or I mean, not the same functions, but the type of problem. So typically you're asked to compute a limit. So find the limit of cosine of x minus sine of squared of x, all that divided by sine of x. And he's asked you in the second midterm, so what should you expect? This problem could be about L'Hopital's rule. But in fact, it is not. It is not about L'Hopital's rule. What was one of the first things that I asked you during that section to do was to check the hypothesis. So cosine of x minus sine squared of x approaches what as x approaches 0? Cosine of 0 is 1. And sine of 0 is 0. So it's 1 minus 0, which is 1. Well, sine of x, which is the denominator, does approach 0 as x goes to 0, but this is not enough. So this goes to 0, but in order to apply L'Hopital's rule, we also need that the numerator is also going to 0 at the same time, which is not the case. So it doesn't apply. And in fact, it's because of this, the numerator has a limit, and the numerator has a limit, but it's 0. That immediately implies that the limit doesn't exist. Okay, so this is kind of a great question, but is asked somewhat often. I mean, this type of question, when you may think that you need to apply L'Hopital's rule, but you don't have to. Okay, so now another problem. Need to ask what happens when you compute the limit as x approaches 0 of e to the x minus 1 divided by sine x. Now actually, well, for this problem we are allowed to apply L'Hopital's rule because e to the x minus 1 goes to 0, so does sine x as x approaches 0. So they both approach 0, so we can apply L'Hopital's rule. And we get that this limit e to the x minus 1 over sine x, as x approaches 0, is equal to the limit as x approaches 0 of the derivative of e to the x minus 1, which is e to the x itself, divided by the derivative of sine, which is cosine. And now we don't have any problem because e to the 0 is 1 and cosine of 0 is 1. So we can evaluate these two continuous expressions and we get 1 over 1, which is 1. Okay. Another question would be, what is the limit as x approaches 0 of a to the x minus 1 divided by x, where a is some positive number, here again, a to the x minus 1 goes to 0 and x goes to 0 both when x approaches 0. Okay, a to the 0 is 1, so this quantity here is going to 0, and if x is going to 0, then certainly x is going to 0. So we can apply L'Hopital's rule now. And that means that this limit is going to be equal to the limit of the derivative. And we saw earlier in class, for the break, what was the derivative of a to the x for a positive constant? And that happened to be the natural log of a times a to the x. All that now divided by the derivative of x, which is 1. And now this function here is continuous. Because, well, it's an exponential function, a to the x. Natural log of a is a constant, so we get natural log of a times a to the 0, which is 1. So in the end, we get just natural log of a. And that's the limit. Typically, during an exam, you will be asked to compute this limit for a particular value of a. So when a is 3 or 2. So it'll give you something like limit of when x goes to 0 of 2 to the x minus 1 over x, in which case the final answer will be natural log of 2. Okay. And so that's it for this application, for this many applications. One thing that seems to provide a lot of trouble for students is the case when you're raising something to a power. So let's try to look at this limit of 1 plus natural log of x to the 1 over x minus 1 as x approaches 1. How do we compute that? Well, we first find that this is actually in the determinant form, so we can actually apply L'Hopital's rule. So this is of the form 1 plus 0, natural log of 1 is 0, over 1 to the 1 over 1 minus 1, which is 0, so this limit will be, okay, so and actually depends on whether you're going to 0 from the right or left. If this is 0 plus or 0 minus. But in any case, it will be 1 to plus or minus infinity. So this is the form of this expression. So it's in the determinant form, 1 to the plus or minus infinity. If you remember now, what is the one thing I advise you to do when we were dealing with, this is some function f of x. 1 plus natural log of x is a function of x, and it's raised to another function of x, 1 over x minus 1. So what was the first thing I recommended you to do? Take the natural log. You should first take the natural log. Okay. So we end up with the natural log of 1 over x minus 1. Remember that the exponent becomes comes down multiplying the natural log of 1 plus the natural log of x. And then, so this is the first step. Take the natural log. Now, this quantity here is going to infinity, and this quantity here is going to 0, because 1 plus natural log of x is going to 1. So natural log of 1 in natural log of 1 is 0. So this thing here is going to 0, and this is going to either plus or minus infinity, depending on whether you're approaching 1 from the right or from the left. So again, this is a L'Hopital's expression, in the L'Hopital's form, one of the L'Hopital's form. And here comes another example. So what did I tell you to do when we had something like this? Well, always leave the natural log alone. Okay? So if you find something like this, whatever you do, just leave the natural log what it is. It turns out that in this case, you don't need to write down, this expression is already given to you in a suitable way, because if you just multiply natural log of 1 plus natural log, 1 plus natural log of x times 1, and write this as a fraction, is already given to you as a fraction with the top and the bottom, then both to 0. Right, so this is going to 0, and this is going to 0. But whatever you do, even if you didn't realize that, you should try to turn what's multiplying natural log into a quotient. To a quotient, so that divides the natural log, and just leave the natural log what it is. So now that we have this, we compute this limit. Now, compute this limit as x approaches 1. This is the initial limit of the natural log of 1 plus natural log of x over x minus 1. And here we can apply L'Hopital's rule. We can take the derivatives of the expression at the top, which is 1 over 1 plus the natural log of x times the derivative of what's inside, which is the derivative of natural log, is 1 over x What about the derivative of the bottom? Well, that's just 1. Excuse me here. I forgot to write down the limit. Alright, so what do we end up with? The limit is x approaches 1 of 1 over x times 1 plus the natural log of x. And here, there's nothing else we need to do. Don't apply L'Hopital's rule again, get 0 over something. Or here 1 is just 1, and x is approaching 1, and 1 plus natural log of x is approaching 1 as well. And these functions are continuous away from where they're not defined. So we can just evaluate here, and we get 1 divided by 1 times 1 plus 0, and it's just equal to 1. Okay, so this is just the limit of the expression when we take logs. So what was the last thing we needed to do? So the limit of 1 plus the natural log of x to the 1 over x minus 1, so x approaches 1. We saw before, it's just e to this limit that we found here. Final step, well, I mean, final thing to do was just to exponentiate e to the 1, which is just e. Okay, so this is it for this problem.